Good afternoon. I'm Carter. I'm a CEO and co-founder of Cameo, and with the Embedded Vision Alliance, I'm helping this track. And I just wanted to introduce Michael Gormish, who's talking about the guts of image compression, but in a different form, influenced by machine learning, which I'm excited to hear about. He's leading research at Clarifai, and he works particularly on classification, visual search, and object detection, but has had a background in everything from JPEG 2000 standardization to impressive 100 patents related to computer vision. So I'm super excited to hear what you've learned about applying machine learning to image compression. So welcome.
Great, thanks. As Carter mentioned, I'm at Clarifai. Clarifai provides a very human-accessible platform for computer vision. We let you run our models if you want, upload images, and we'll tell you if it's safe for work or not, safe to post on your website. We also let you build your own models or upload your data and search through that and deploy things for you if you want to scale your models to large size but don't want to run your own infrastructure. We'll take care of that as well. We don't do compression. As Carter mentioned, that was something that I did for a long time and was sort of curious to catch back up and see what's going on. Because as you've seen at Embedded Vision Summit, machine learning is replacing traditional computer vision in all sorts of areas. So image classification and object detection, we see that on the show floor everywhere. Everyone is doing that with not the traditional mechanisms that used to be used, but with machine learning. But also things like image matching is now done typically with machine learning rather than a set of features that are matched with a ransack algorithm. And even things like pose estimation, which you would think is a very geometrically oriented problem and wouldn't respond well to just saying, oh, here's an example and here's the pose that I want you to respond with. Even that has had success with machine learning techniques. And so there's a large focus now on, rather than working out the mathematics, just providing enough data and collecting the data or synthesizing the data and generating the right answer. And so I wanted to look back at image compression and say, well, what's the progress there? So traditionally, image compression has this very simple block diagram. There's an input image on one end, there's a code stream on the other end, and the first thing you do is usually some sort of color transform. I'm going to go from RGB color space to YCRCB in the case of JPEG, and try to remove correlation that happens across color bands. Then there's a spatial decorrelating transform. So in JPEG, that's the discrete cosine transform. In JPEG 2000, that's the wavelet transform. Again, I'm trying to remove redundancy. So things that happen a lot, I concentrate into just a few coefficients. And both of those stages, while they could be implemented losslessly, they typically have just a slight loss because they have some floating point approximation. But in general, that's not where any loss comes from in image compression. So there's usually an explicit stage, a quantization stage, where I take these coefficients and I divide them by something. And that's where my loss occurs, and I try to do that intelligently so that the loss that does occur is something that the human visual system doesn't see. And then finally, there's a stage that's entropy coding, and that's a lossless stage, but it's basically taking a sequence of coefficients and turning it into a very compact bit stream by having an estimate of what's the probability that I'm going to see a 0 or a 1, and coding that close to the entropy. All of these stages were, in traditional image compression, very carefully hand designed, and lots of hand experiments to see which quantization works well with which decorrelating transform, how can I tweak the reconstruction values to get the best quality. And so here's a list of many compression methods. The top two only have the entropy coder stage, so they tend to work best on more graphic images rather than natural images. But the bottom starting with JPEG and going all the way through. The rest of those are all block coders. They divide your image up into blocks. They do these decorrelating transforms on them. They do some sort of quantization, and they do some sort of entropy coding. So they all follow the exact same pattern, but we've gotten better and better and better at doing those patterns. So the compression has gotten better over the years. However, image compression is a natural topic for machine learning. In the late 80s, I was in grad school, and we would look at vector quantization, which is essentially machine learning on a scale, and you could prove, in fact, under certain circumstances, that vector quantization is an optimal compression system. Of course, you have to prove that, you have to allow the size of your blocks and your vectors to go to infinity, but at least it's provably optimal, which none of the other compression systems that we currently use are. At the same time, while I was in grad school in the late 80s, there were autoencoders. People were studying neural networks, and they would take an input and they'd try to reduce it to some intermediate representation and then recreate that on the other end. So again, image compression is a natural thing that falls exactly into this pattern. And so now, today, what's the state? The great thing about machine learned image compression is we don't have all this data labeling problem that the previous two talks in this room have talked about, right? We don't have to hand label anything. All we need is an original image or lots of original images, and the desired output is the same image. So the only thing we need to do is penalize the size of the representation in the middle, and we don't need to label any data. So we have tons and tons of data. We should be able to do very, very well with machine learned image compression. And indeed you can, right? So here are some examples of things that have been done with various machine learned image compression. So the picture of the faces, there's a JPEG 2000 compressed face at 30:1 compression, and a machine learned image compression with 180:1 compression. On the right-hand side, there's a natural scene, and the bottom four images are all block-based, traditional, hand-tuned compressors, and they all have a variety of artifacts that I think you can probably see even on the screen at this distance. And in the upper right-hand corner, at one of the lowest bit rates, is a machine-learned image compression system that it's arguably better than the ones below it. And so you'll see this in dozens and dozens of papers. They will take a typical they'll take a typical traditional image compression system, push it to the point where you can see the artifacts, and then find a machine-learned system where, they can show better artifacts. But one of the things that always drives me crazy about these papers is I never use these standards at those bit rates. And I would never use a machine-learned image compression standard at that bit rate either, because it's not an accurate representation of my original image. I want to operate at a much higher bit rate where the quality is perceptually lossless. And I can do that right now with JPEG and JPEG 2000. Of course, it's harder to publish how I'm looking better unless I push those algorithms that already exist to the point where they're starting to break down. There are fun things that happen with machine-learned image compression, though. So one of the things that happens with JPEG and with JPEG 2000 when you push them to the extremes is you see these weird screen patterns or ringing patterns. In machine-learned image compression, you can see changes of content rather than sort of changes in quality. So all three of these images look like they have about the same subjective quality. Yes, there's some little streaks in the sky, and the face doesn't look exactly right, but they all sort of look like they're the same level of blurriness, and they're the same level of pixelation. But as the compression has increased, the content has changed. So apparently, if you train your machine-learned image compression system, it's easier to represent a face without glasses than a face with glasses. And so we can save bits by taking the glasses off. And it's apparently easier to represent a scene that has a sky and ground but no mountain than it is to represent a scene with a sky and a mountain and ground. And so as you crank up the image compression on some of these systems, you can get actual changes of the content. Maybe this is fine. Maybe this is fine for video games or some sort of simulated environment. But again, I don't think you would want any of these images as a representation of reality. You wouldn't want to be storing your passport photo at the quality that's provided by this system. Now, thankfully, you can experiment with this on your own, and you can do it just by checking out a repo from the TensorFlow repo in the research directory. And so Google, Nick Johnson and others listed here, did this very wonderful paper where they said, okay, here's a machine-learned image compression system, and we'll give you the description in the paper, we'll give you the model, and you can play with it. So that's nice. And one of the nice things about this paper is it allows you to operate at a variety of bit rates. So this particular algorithm produces 1-bit representation at a very low quality, and then it continues to improve that image by producing bit streams that are differential images. So, okay, I want to get the next level of quality. I've got basically a difference image that I can decode and put on top of that and get a better quality image. And so then I can keep going, and at least with this system, I can do some real comparisons and say, if I drive the quality high enough to a point where I would really care about using this image, how does it compare? And so we'll see how this comes across on this monitor. I guess as I look at the screen, I can definitely see here's a JPEG at a very low bit rate, and you'll see the kind of artifacts that it has. It has some large blocks, and it in the smooth areas, and the detail is completely gone in the trees. And as we add a few more, let's see, was that obvious that there were more bits added? I have to make sure. Yeah, okay, so I definitely lost some of the blocking in the sky now. And yeah, actually that looks pretty good on this monitor. I'm surprised I don't even see the typical ringing through the projection system. There's definitely clearly some artifacts where the smooth areas meet, but not the typical JPEG artifacts anymore. So this is getting close to where you might actually use JPEG. And then we can do the same thing with the machine learned system. We can run it at a very low bit rate, and we'll see this algorithm has a more pixelated feel, or it feels like the air is distributed across the image and not so much changing the content like the other algorithm was. But I think that's in part because it's a structured system, so I can make errors across the image, and now I can add to the place where those errors are and improve things. So as I go from 1/8 of a bit per pixel to 1/4 bit per pixel to 3/8 of a bit per pixel, I get some improvements in quality. And so what's typical, you can really measure peak signal to noise ratio and JPEG compression and bit rate, and you can plot rate distortion curves like I did when I was on the JPEG and JPEG 2000 committee. And the best machine learned image compression systems will come out on top of the best JPEG or JPEG 2000 system. So they are better systems now than the JPEG 2000 system that I worked on. And they're even better if you use not PSNR, but if you use something like the structural similarity metric, because you can use other things. It was possible to tune JPEG for mean squared error, but much harder to tune JPEG for harder image quality metrics. Now there are much, much better image quality metrics that take into account regions rather than single pixels and the errors that you're likely to pick up there. And so you can train machine learned compression for these better error metrics and do even better. Now I should mention that as I was proofing my slides this morning, I realized that the points I've plotted on this graph are actually wrong. And that was because I didn't run, when I was generating the machine learned system, I didn't run the entropy codec piece, I just ran the autoencoder piece. This particular graph is wrong, but it is possible to do, if you include the entropy coder, you do really see that the machine learned compression system is outperforming the JPEG or the JPEG 2000. And I'll get to that. I'll get to some other examples where we see some real numbers on that. So why does machine learned compression do better? Well, part of that answer is it has a lot more basis functions to work with. It has a lot more room to work with. So JPEG is very simple. It works on 8x8 blocks. And in fact, there's really only 8 basis functions. So there's DC and there's high frequency over the an 8-point transform. And in fact, that happens in 2 dimensions. So on the left side of this figure, you can see the 2D separable 8x8 DCT. They're basically all images are decomposed into these 64 little sub-images and then quantized and recombined. And that's all JPEG has to work with. Machine learning compression has a lot more basis functions. It's not limited to 8 points in either direction. They're overlapping and they're able to be learned from the data so they can be more representative of natural imagery, and they can operate at different levels. And so you do see in a machine learned system, some of the neurons are firing on patterns that look something like the DCT coefficient vectors at low levels of the network, but at higher levels of the network, there's more structure and more things that are being picked up by the system. Now, this improved performance comes at a huge computational cost, right? So in the era of JPEG, we worked very, very hard in my lab to try to reduce the number of adds and multiplies it would take to do an 8-point or a 64-point transform for the JPEG block. In fact, if you played tricks and were very smart, you could remove almost all of the multiplications and combine those with the quantization. So you were going to do some level of quantization in the JPEG algorithm on every coefficient anyway, because that was how you were getting your actual compression, was to divide by some value depending on the frequency of what you were looking at. So you're required to do 1 multiplication per coefficient, which is the same as the number of pixels. So 1 multiplication per pixel for quantization. And for the DCT, you could basically get it to where it was 1 extra multiplication per pixel. And so you can do image compression with 2 multiplies per pixel. Now compare that to a neural network. Neural network, so I've exaggerated in this case. I've used an 11 by 11 convolutional layer where in fact you might use a much smaller one, but if you were using a network that had an 11 by 11 convolutional layer and it had a stride of 4, so it was doing this every 4 pixels, there would be 7.5 multiplies per pixel per channel. So if your network had multiple channels, which it does, that's part of the deep neural networks, the convolutional neural networks, is they have lots and lots of channels. And so there are not tens, but hundreds or thousands of multiplies per pixel in a machine-learned image compression technique. Likewise, you can look at what does, at the higher levels of the network, if I have some sort of 4,000-point fully connected layer, that alone turns into multiple hundreds of multiplies per pixel. And so is this borne out in reality? Well, here's a totally unfair comparison where I ran JPEG on my image, I ran JPEG 2000 on my image, and I ran this machine-learned compression system on my image. And I know it's totally unfair because I worked very hard on the JPEG 2000 standard, and it's not really 10 times slower than JPEG, it's only 3 times slower than JPEG. So it's not as bad as things would appear. But on my system, out of the box right now, I can run JPEG on 1 image in 26 milliseconds and encode it using 1 core of the CPU, and I can run the machine learned image compression on 4 cores of the CPU. I'm not using the GPU, so that is sort of biasing things against machine learning because I haven't made use of that GPU that was sitting idle, maybe. And I'll spend 10,000 times as long on this. So again, that's not a fair comparison, but it does sort of match my sort of order of magnitude thinking about, okay, here's the network and the number of multiplies that have to be done in the different stages. And, but I wasn't going to go to the trouble to try to tune each of these systems. Fortunately, there's a contest going on. There's a machine learned image compression workshop that happens in conjunction with the CVPR conference. And these are results from last year. And they are working on quality. And so you'll see that JPEG is down at the bottom on the quality. So there's a column labeled PSNR, and JPEG is down at the bottom, and the machine learned systems are on top. And there's another column, MS-SIM, which is the structural similarity. So that's a better metric to measure quality. And again, JPEG will be down at the bottom, and the machine learned systems will be up at the top. And there is an award at this conference if you can get into the top 5 in quality for speed. But the top codec is 113 times slower than JPEG. So people are here at least paying a little bit of attention to speed. And the top codec is a 97 megabyte model. So the size of that compression engine is perhaps more than you want to consider for an embedded system right now. This contest is being repeated this year. I checked the results this morning. It's not done. They haven't finalized them, but the leaderboard is live. And so right now, the top coder, I think, is 47 times slower than JPEG. So the gap is closing. But I think it grew to 250 megabytes, so the size of the codec is increasing. So I guess it's a wider, shallower network or something. The other thing I think that's important to keep in mind is that image compression is an interchange format. So when we designed the JPEG 2000 standard, it was very important that you'd be able to decode the image the same way in multiple places, and you had to have a common agreement on the interchange format. You had to be able to handle any size image, any number of components, any depth. And the machine learned systems that you'll find in the academic papers certainly aren't there yet. They're not trained on a comprehensive data set. They're trained on a data set that they want to match to hit the leaderboard. And some of them only work on multiples of 64 by 64 images. And most critically, a lot of them only work at 1 or 2 bit rates. So I haven't been tremendously encouraged by the state of machine learning compression. I mean, it's the best in quality, and I think the speed will get better. But I am left wondering, is there something else we can do? And it depends, right? So if you have a system, it's possible to use traditional image compression still in the middle of that system. And then maybe, depending on where your computation is and where your time is available, you can do machine learning either pre-processing or post-processing, and you can do a lot better that way. So for example, on the top, there's a set of images, and underneath is a machine learned image saliency map. And you can use such a map with any traditional image compression system. It's a little bit harder with something like JPEG, where it's harder to change the quantization values from block to block. But for other systems, like the H.264 systems, you can have different levels of quantization that happen and change as you go across the image spatially. So you can use machine learning to improve a traditional image compressor on the compression side. Alternatively, maybe you want your camera to be very cheap and you don't want to spend the GPU or the CPU cycles to do intensive processing on the input side. You can use machine learning on the post-processing side. So all those artifacts that we see if we drive JPEG to the extremes, when I see the block boundaries and things, and I can look at an image and I can say, that's a JPEG artifact. I know that was compressed with JPEG. Well, that's a perfect situation for machine learning to learn to correct JPEG artifacts and make it look more like an actual image would look than an image that had gone through a JPEG compression system. So then I can use the JPEG compressor on the inside, and then when I get the image out, and maybe only when I care about it, I can do the machine learning stage where I've decided to improve the reconstructed image. So, is machine learned image compression ready for real time? Well, the conclusion is it is the best quality per bit. So if you want the best quality per bit and you have a large budget for computation and energy and memory, then maybe. But you also have to deal with the fact that the systems currently lack flexibility in an interchange system. So in general, the answer is no. Machine learned image compression is not ready for prime time. But there are special use cases that may make it that way. And there's contests in play. Maybe we'll see some level of capability in a year or two that allows us to do better and be competitive computationally. And then this last page is some papers and references to evaluation metrics and things that are interest for both of these systems. So, that's it. Thanks.